So, are you ready?
Yeah, I'm ready.
Hey, Sam, have you ever met anyone with exactly the same name as you?
I've met some Sams, of course, but none with the same surname as me.
I'm not surprised, but let me tell you a story. It happened way back in July 1900. The Italian king Umberto I met another man whose name was also Umberto. He was a restaurant owner. Amazingly enough, the two men looked identical. It turns out they were both born on the same day at the same time. They were married in the same month of the same year, and their wives were both called Maria. The day the restaurant opened was the day the king acceded to the throne. Moreover, the restaurant owner had a son called Vittorio. The prince was also called Vittorio.
That's really an unbelievable coincidence. The chance of it occurring must be less than 1 in 10,000.
1 in 10,000. That's just a 10,000th. So you're using a very small number here to express the rare chance of an event occurring. In mathematics, we also use a number to represent the chance of an event occurring. This number is called probability.
So how do we use a number to represent chance in mathematics?
Well, maybe I can explain it to you with this tombola cage. We have here some green and white balls. We put all the balls in the tombola cage. And if a green ball comes out, you win a prize. What's the chances of getting a prize related to here?
The chance of getting a prize is related to the total number of balls and is also related to the number of green balls.
That's correct. Now consider this. We'll take a total of 10 balls, of which 3 are green. If we compare the number of green balls, 3, with the total number of balls, 10, we obtain a ratio of 3 to 10, which represents our chance of winning a prize. That's to say, the probability of winning is 3 over 10. In maths, winning a prize is called an event. It's usually denoted by the letter E. Probability is usually denoted by the letter P. Therefore, the probability of winning a prize can be denoted by this symbol. Since a total of 10 balls may be extracted from the tombola cage, 10 is the total number of possible outcomes. And as there are 3 green balls in all, 3 different results can give rise to a prize being won. Therefore, 3 is the number of outcomes giving rise to a prize being won. Here, therefore, is the formula of probability. Using the formula to calculate probability, we must make sure that every single outcome possesses an equal chance of occurring. Now, if there are no green balls, what is the probability of winning a prize?
Of a total of 10 balls, 0 balls can result in winning a prize. Comparing 0 with 10, the probability of winning a prize is 0.
As no balls can result in a prize, winning is impossible. So the probability of an impossible event is 0. Let's change things around. Here, all 10 balls are green. What's the probability of winning a prize now?
If we compare the number of green balls, 10, with the total number of balls, 10, we obtain 1.
That's right. As all the balls are green, winning a prize is certain. So the probability of a certain event is 1. That is to say, for the probability of an event, the smallest value is 0 and the greatest 1. Therefore, probability can be any number between 0 and 1.
Hey! Come on, come here!
What is it?
What is it?
I've got an idea! Why don't we play a game of dice?
A game of dice?
Yes, and whoever wins on the throw of the die can take the fruit of his choice, all right?
A fruit? All right, what are the rules of the game?
If the die is thrown and the number's less than 3, then Smarty here wins. If the number's 3, then Biggie wins. If it's greater than 3, then I'm the winner, all right? Shall we play? Mm-hmm. Then let's go! I win! Now your turn.
I hope I win.
My turn.
Looks like I win again.
Ah! I win again! A banana!
Oh, look, it's a tree! No, wait, look at yours and look at mine. Hey, this game isn't fair.
Yeah, he's right!
It is? What are you talking about? Each time a die rolls, there can be 3 outcomes. They're smaller than 3, 3, and greater than 3. So it's plain to see the chance of each one of us winning is 1/3. You see, it's fair.
Do you think it's reasonable, what that crafty clown said?
No, I don't think it's reasonable. In throwing a die, 1 to 6 may come out. There are 6 outcomes in total. For a result smaller than 3, there are 2 possible outcomes, 1 and 2. For a result of 3, just 1 outcome is possible, 3. For a result greater than 3, 3 outcomes, 4, 5, and 6 are possible. Therefore, the probabilities of these 3 cases are 2/6, 1/6, and 3/6 respectively. The probabilities of these events aren't equal. The clown chose the rolls with the greatest probability. The game wasn't fair.
That's correct.
Hey, look, a viewer sent in a question. There's a photo attached to it. It's a photo of him and his 6 brothers taken when they were young. His mother gave birth to 7 boys in a row. He's asking, what is the probability of giving birth to 7 boys in a row?
It's a very interesting question. I think to make it easier, I'll start with a case of a family with 2 or 3 children. Let's start with a family with 2 children. The first child could be a boy or a girl. If the first one is a boy, the second could either be a boy or a girl. Likewise, if the first one's a girl, the second could either be a boy or a girl. If we list the combinations of 2 children, we obtain these combinations: boy, 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 girl, girl, boy, and girl, girl. Therefore, we have a total of 4 possible combinations. Only one of these combinations involves 2 boys. Therefore, the probability of having 2 boys is 1/4. If the parents then decide to go on and have a 3rd child, then no matter which combination the first 2 is, the 3rd child could either be a boy or a girl. Just like before, if we make a list of all the possible combinations, we obtain these 8 combinations. We can see there is only one combination involving 3 boys. Therefore, the probability of having 3 boys is 1/8. If we take these results and add them to the table, we can see a pattern appear. If we apply the same pattern to the 7th child, the probability of having 7 boys is now 1/2 to the power of 7. That is 1/128, or approximately 0.0078, a very small probability.
I thought it was going to be difficult, but the way you explained it, it seems to be easy.
That's because I was using a tree diagram.
Hey! Hey guys, over here!
What is it now?
Yeah!
I've got a good idea. Why don't we play another game of dice?
You want us to play another game?
No way, forget it. I'm not playing with you. The last game wasn't fair.
But I didn't think it over last time. This time it'll be fair, I promise. Now, if you throw the die and get a number 1 or 4, then you'll be the winner. If you get a 2 or 5, well, then you'll be the winner. And if I get 3 or 6, of course, I'll be the winner. Each of us has a probability of 2/6 of winning, so now it's fair. You can throw first.
All right.
Right, now it's your turn.
Oh.
Here. Now it's my turn.
I want to throw again. Oh, I lost.
Come on, it's my turn. Ooh.
You won the most fruit again.
That's right.
Beginner's luck.
Oh.
Hey, you know, I'm really tired. I'll take a rest.
Why does he win all the time? It isn't fair. Strange. Oh. There must be something up with this die. I've thrown the die 200 times. If the die is fair, then each result should have roughly the same number of occurrences. But look here, the 6 comes up far more often than any of the other numbers. This die is not a fair one.
The yellow clown was pretty smart. He was able to test the fairness of the die by an experiment. So then, from this experiment, we can also estimate the probability of all the other numbers. For example, to estimate the probability of the 6 occurring, as in the clown's 200 throws, the 6 came out 81 times. We compare the 81 with the 200 and can estimate the probability of the 6 occurring as 81 over 200. Using the same method, we can also estimate the probability of all the other numbers occurring. Since these probabilities have been worked out by experiment, we call them experimental probabilities. So there's experimental probability and calculated probability. We see the relation in this data on coin tossing.
Okay.
Experiments 1, 2, 3, 4, and 5. In an experiment, when the number of times heads came up is divided by the number of tosses, the experimental probability is obtained. From the table, we see that as the number of tosses increased, the experimental probability and the theoretical probability 0.5 match more closely.
Wake up! Hey, I know! Let's play the die throwing game again.
Not the dice throwing game again.
All right, but I say we change the rules this time.
Really?
Yes, whoever throws the highest can take all the fruit that's on the table, right?
If you want, but it won't be easy for you two to beat me, though.
Come on, let's throw it.
All right, let's go. Huh? See? A 6, a 6. I told you it wouldn't be easy to beat me, didn't I?
It's my turn now. We'll see.
Look, he's thrown a 7.
A 7! That means I'm the winner.
Huh? How did you do that? How'd you throw a 7?
Oh, easy. I just did the same as you.
Oh, you mean he cheated us?
No! I gotta be going now. Have some fruit here.
Hey, come back! Come back here!